Okay, most probable position, right, of finding electrons in 2s orbital. In 2s orbital of hydrogen atom. Okay. Yeah, actually, this requires a lengthy calculation. So, I have given you the procedure to do this. Okay, but I'm not going to solve this actually. Actually, it's a lengthy procedure, right? It is available in books. So, what I'm going to do is give you the methodology, right? How to work out. Listen, the radial part of the wave function, the actual radial part of the wave function, right, can be given as radial function for 2s orbital can be given as it consists of a normalization constant. Okay, let me write this as n0 into 2 minus r by a naught into e power minus r by 2 into a naught. Okay, this is the radial part of the wave function for 2s orbital. And if you take the square, there is no imaginary part. So we can take square to get the probability. So probability n naught square, I'll take it as n, and 2 minus r by a naught the whole square into e power. If you take the square, you get minus 2r by 2a naught, 2 cancel, so you get e power minus r by a naught. Okay, this is the probability density. What is the radial probability density? We have to find out the radial probability density for 2s orbital. Okay, this is radial probability density, which is nothing but 4 pi r square into this quantity. That is the probability at a particular distance r. Okay, now what I am going to do. So the radial probability distribution, right? You'll get this particular function. To get the maximum, we have to differentiate this. Okay, so differentiate this radial probability distribution, right, and put the value equal to 0. Okay, listen. And put the value equal to 0. If you substitute the value equal to 0, then we can find at what distance. Okay, see, we plot probability for 2s orbital versus r. First, we get a small maxima, right, a small peak. Then we'll get another peak which goes like this. And this is the maximum. This gives you the most probable position of finding electron. And what is this value actually? RMP. RMP for 2s orbital. Okay. RMP for electron present in 2s orbital is equal to. Right. Listen. This is actually a somewhat lengthy calculation. I'm not going to do. Right. But I showed yesterday. I showed you the methodology. Okay. But I'm not going to do that now. So I'll give you the final answer. The final answer is 3 plus square root of 5 times a naught. This is the RMP value to find the most probable position of electron in 2s orbital of hydrogen atom. Okay. This position, where probability is 0, this position is nothing but equal to 2 times a naught. So at 2 times a naught, we get a node. So in 2s orbital, the radial node is present at 2 times Bohr radius. Okay, you know very well, a naught is nothing but Bohr radius. Bohr radius. So at 2 times a naught, we get the node. And what is the RMP? RMP value is just beyond this node, which is actually 3 plus square root of 5 into a naught. Okay, if you differentiate this and put the value equal to 0, you will get this RMP. Okay, take the we will discuss now. So the next point is how to find the average distance, right, of electron present in any state. Okay, any state say represented as psi m. Any state. Okay, the average distance is equal. It may be 1s orbital or 2s orbital. Okay, 2px, 2p, whatever it is. You can find the average value of R using the formula A0 by 2 into Z, okay, into 3n square minus L into L plus 1. This is the formula we use to calculate average distance of electron, okay, present from the nucleus. Okay, tell me what is the average value of R for electron present in the 1s orbital of hydrogen atom. For hydrogen atom, Z is 1, N value, see here, N value is 1, so put N value equal to 1. For S orbital, L value is 0. See, N value 1, L value 0. L value 0, this becomes 0. Yes. What's the answer?
3 A0 by 2. A0.
Very good. So, 3 A0 by, this is for average value of R for 1s orbital. Similarly, average value of R of electron present in 2s orbital, okay, if you do it, you will get the answer as 6 times A0. Okay, just check it. The average value of nth power of the distance of electron from the nucleus in the ground state of hydrogen atom. See, how to find average value of nth power of distance. It may be, if n is 1, you will get average value of R. If n is equal to 2, then you will get average value of R square. Listen, so what I am going to do now, listen, this is nothing but average value, the average value of the nth power of the distance of the electron from the nucleus. In the ground state of hydrogen atom. This is very important. In the ground state means 1s orbital. In the ground state of hydrogen atom. Okay. Listen, for the ground state, if electron is present in 1s orbital of hydrogen atom, then to find the average value of R power n, okay, you can use this formula. Is equal to gamma, it's a gamma function.
Voice break up, sir.
1 second. Okay, so it is a gamma function of n plus 3, gamma function of n plus 3 divided by 2 to the power n plus 1 into Bohr radius power n. This is the formula. Okay, take it. Actually, gamma function is an integral. Okay, let me write the gamma function first. Gamma function of any number n, right? It is actually an integral. What is the integral? Integral 0 to infinity x to the power n minus 1 into e power minus x into dx. Here n should be greater than 1. If n is greater than 1, then this integral is called as gamma function of n. This integral is called as gamma function of n. Okay. And how to find the value of the integral? Listen carefully. Suppose you have gamma function of n plus 1. Gamma function of n plus 1 is nothing but n factorial. Okay, you need not find the integral. It is actually simplified and it is given in a simplified form called gamma function. So gamma function of n plus 1 is equal to n factorial. What is gamma function of n then? Gamma function of n. If n plus 1 is n factorial, what is n?
N minus 1 factorial.
N minus 1 factorial. Okay, what is the gamma function of 1? Anyone? Gamma function of 1.
0, sir.
0 factorial. What is 0 factorial?
1.
1. So gamma function of 1 is 1. Right? And this is very important. Gamma function of 1 by 2. Gamma function of 1 by 2 is square root of pi. Okay? Just note down. Now our goal is to find average value of R, R square, R cube and all. How to find average value of R? Just now I gave you the formula, right? Right? What is the formula? Average value of R power n is equal to gamma function of n plus 3
n plus 3
by 2 to the power
n plus
n
1
plus
power
1
n plus 1
into
a naught
Bohr
power
radius power n, right? Bohr radius power n. This is the formula. But this formula is applicable only for 1s orbital of hydrogen atom, ground state of hydrogen atom. Okay. Now here I have given r power 1. So n value is 1. Put n value 1 here. 3 plus 1 4. Why? Put n value 1 here. 1 plus 1 2. 2 square into a naught power 1. Wherever n is there, put n equal to 1. What is the gamma function of 4? Anyone?
3 sir.
3 factorial. Yes, good. Gamma function of 4 is 3 factorial. But 2 square is 4 into a naught. A naught power 1 is a naught. What is 3 factorial? 3 into 2 into 1.
6
A naught. I can cancel 1 to 2, 2 to 4. So what's the answer?
3 by 2 a naught.
We have already got this answer, right? See? Average value of r power 2 for the ground state of hydrogen atom. Okay. Yes. Tell me what's the idea? Just use this formula. Now n value is 2. N value is 2. Put n value 2 in the formula. So gamma function of 2 plus 3.
5
5
sir.
sir.
5. Then 2 power. N value is
2
2.
power 3
2 power 3. Very good. A naught power
3 a naught power square
2. Correct. What is gamma function of? This is not square root. Remember, this is not square root. This is gamma function of 5. What is gamma function of 5?
4 factorial.
factorial.
4 factorial. What is 4 factorial? 4 into 3 into
3
2
into 2 into 1
What is 2 cube?
8 sir.
8.
2 into 2 into 2
Correct. 2 cube is 8. Yeah. So 4 into 2, 8. So you can cancel 8 and 8 here. So what's the answer?
3 a naught square
3 a naught square. This is the average value of r square for the electron present in the ground state of hydrogen atom. Okay. Take note. The next one is about virial theorem. Take note. Virial. Take note. Virial theorem. Right. Listen. This virial theorem is very useful to find the expectation or average value of potential energy and the average value of kinetic energy. We can compare them actually. Okay, we can compare these two. According to virial theorem, according to virial theorem, observe carefully. According to virial theorem, average value of kinetic energy, right? Average value of kinetic energy is equal to some number s by 2
s by 2
by 2
into average value of potential energy. Okay, yes, we already discussed this problem. We already discussed this problem under simple harmonic oscillator. Okay, yes, I am using the same formula. But now I am going to use this formula for hydrogen atom. Okay, and I also told you, listen, the sum of kinetic energy, average kinetic energy, and the sum of average kinetic energy and average potential energy, the sum is equal to average of the total energy. Remember, the wave functions, right, for hydrogen atom, the wave functions are eigenfunctions of Hamiltonian operator. Therefore, average value of total energy is nothing but the energy. This is applicable for any nth state. This is applicable for any nth state. This formula is not only applicable for hydrogen atom, it is even applicable for simple harmonic oscillator. For any nth state, you can use this formula. Right? Now listen, in the case of hydrogen atom, so carefully, in the case of hydrogen atom, what is the formula for potential energy? Potential energy depends on the variable R, which is given as, see, nucleus charge is, for hydrogen atom, nucleus charge is plus E, electron charge is minus E, distance between the nucleus and the electron is R. So, what is the potential energy? Multiply the two charges minus E square by permittivity of the medium 4 pi epsilon naught divided by distance. This gives you the potential energy. Here see E square 4 pi epsilon naught, these are all constant. So I can write this equation potential energy as is directly proportional to minus, bring this r power 1 to the numerator, so we'll get r power minus
R power minus 1.
minus 1. Okay, listen, don't worry about this minus sign and all, see the power alone. The power will give you the value of S. Okay, so don't worry about this minus, right? So here I have r power plus 1. If I bring this r power plus 1 to the numerator, we will get r power minus 1. And that gives you the value of S. So S is equal to minus 1 in the case of hydrogen atom. Now, if we put S is equal to minus 1 here, we get the relation between average kinetic energy and average potential energy for hydrogen atom. Let me do it here. So, for hydrogen atom, right, the average kinetic energy is equal to minus, S value is minus, so minus 1. So, I'll put minus 1 here. So, minus 1 by 2 into average value of potential energy. Okay, remember this is very, very important for hydrogen atom. Right, now listen, suppose I want to know what is the potential energy of electron present in the 1s orbital. What is the average potential energy of electron present in 1s orbital? How to do that? Very simple. Listen, we know very well average kinetic energy, let me write T is kinetic energy. Average kinetic energy equal to S by S plus 2 into energy, total energy of the electron in the nth state. Okay, similarly, average potential energy equal to 2 by S plus 2 into total energy in the nth state. Okay, take this. So this is the energy formula, energy of the nth state of hydrogen atom in atomic unit. It is n square by 2n square. Okay, take it. Okay, yeah. So for hydrogen atom in the 1s orbital, what is the energy? Put n equal to 1 here. So hydrogen atom Z is 1. So 1 square is 1. Here also 1. So we get minus 1 by 2 atomic unit. This is the energy of the electron in the 1s orbital. Now what is the potential energy, average potential energy in the 1s orbital? You know very well. Average potential energy, I have given the formula already. How it is related to average potential, how it is related to total energy.
2 by S plus 2 into E.
Yeah, so I will use the formula 2 by S value is minus 1, correct?
Minus 1.
Minus 1 plus 2 into energy of the 1s orbital. Okay, E1. Right? So 2 by minus 1 plus 2 will give 1 into energy of the ground state is minus 1 by 2. So what's the answer?
Minus 1.
Yes, average potential energy in the 1s orbital is minus 1 atomic unit. Okay, take it. What is the average kinetic energy of the electron in the 1s orbital of hydrogen atom? What is the relation between kinetic energy? What is the relation between kinetic energy and potential energy according to Briere theorem? According to Briere theorem,
minus 1 by 2.
Minus 1 by 2.
Potential energy.
Okay, S value is minus 1. So minus 1 by 2 into V. Minus 1 by 2 into average potential energy. Average potential energy is minus 1 for 1s orbital. So minus 1 into minus plus 1 by 2 atomic unit. Okay, take it. It's very simple but very, very useful. So now we need to find out what is the average potential energy and average kinetic energy of electron present in 2s orbital of hydrogen atom. Okay, this is how to do that. First we calculate the total energy. Total energy for the n equal to 2 level. Okay, n value is 2 now. So total energy for the n equal to 2 level is equal to minus hydrogen atom Z value is 1. So 1 by 2 into 2n square, correct? So let me write the formula. En equal to minus Z square by 2 into n square. You will get the energy in atomic unit for hydrogen atom. For hydrogen atom, Z value is 1, so put 1. Now n value is 2. N value is 2, so 2 square is 4. So what's the answer?
Minus 1 by 8.
8 atomic unit. Atomic. This is the This is the total energy of the electron in the n is equal to 2 level. Total energy of the electron in the n equal to 2 level. And the energy is given in atomic unit. And you know very well, 1 atomic unit equal to 27.21 electron volt. Remember this. So if you want to convert atomic unit into electron volt, you can use this relation. 1 atomic unit equal to 27.21 electron volt. Now listen, we've calculated total energy. How to find the average potential energy? Average potential energy of the electron in the 2s orbital. You know very well, average potential energy equal to, what is the formula? 2 by S plus 2 into
E
total energy of the
E2.
electron in the second level. Okay. So, and S value is minus 1. So, what we get? S value is minus 1 plus 2. Correct. S value is minus 1. Minus 1 plus 2 is 1. Into E2 value we found out minus 1 by 8.
Minus 1 by 8.
So, what's the
minus
answer?
1 by 4.
That's all. Thank you. So, average kinetic energy of electron in the 2s orbital is equal to S by 2. S value is minus 1, so minus 1 by 2 into average value of potential energy in the 2s orbital. And we found out the average value of potential in the 2s orbital is minus 1 by 4. So, minus 1 by 2 into minus 1 by 4. Right. So, we'll get the answer as 1 by 8 atomic unit. Right. Take it. Listen, for multi-electron systems, or many electron system. Right. Let me use the word many electron systems. For many electron system, it is very difficult to solve the Schrodinger equation. Okay, so for many electron system, if you want to solve H psi equal to E psi, right? Okay, it's very tough, difficult. I can say cannot. It's not possible. Not possible. Possible without approximation. Without approximation is not possible. But using approximation we can solve. Okay, so what are the approximate methods we have? We can solve the Schrodinger equation using approximate methods. Approximate methods in quantum chemistry. What are the approximate methods we have? Isn't actually in chemistry we follow these two techniques, approximate methods. One is variation method. The other one is perturbation method. Variation method and the other one is perturbation method. These two are the major approximate methods we use in quantum chemistry. Right? See, according to variation method, the average value of energy, average value of energy for a particle in a particular state psi. Okay, the particle is present or the system is present in some state psi. In that state, what is the average value of the energy? Listen, I'll write the average value of energy simply like this, epsilon. I'll put the epsilon symbol which indicate average value of energy or variation energy. Okay, energy calculated using variation method. Right, which is equal to, right, listen, trial function, right, H operator, trial function divided by trial function. This is the formula we use to calculate average value of energy, right? And this is the method to calculate average value of energy by variation method. Okay. For this method, what is required is the trial wave function. Listen, what is Phi? Phi is called trial wave function. What is mean by that? For a given system, we should guess a wave function, okay, for a particular state, right? Trial wave function, we should guess some wave function. Listen, trial wave function need not be accurate, right? It may be approximately okay, right? So we should guess some trial wave function, but the very important condition is that the trial wave function should obey boundary condition of the formula. It should obey the boundary condition. So while choosing the trial wave function, okay, you should be little careful that wave function should obey the boundary condition of the problem. Okay, what are the steps we should follow? Step 1. For a given system, okay, find the trial wave function. That's the step 1. For the given system, find the trial wave function, or give or guess some trial wave function which should obey the boundary condition of the problem. Then what is step 2? Step 2. Using that trial wave function, calculate the expectation energy E. Using the trial wave function, calculate the expectation energy E. Right. This is expectation energy. This is very important. While choosing the trial wave function, okay, you should include some parameters, right, called variation parameters. You should choose or you should guess a trial wave function that contains some variation parameters. Parameters are usually denoted as alpha or beta or C1, C2, etc. Okay, variation parameters. Now listen, the expectation energy that we calculate using the trial wave function, that depends on these parameters. Okay, at one particular value of the parameter, the expectation energy reaches the minimum. So what is step 3? Step 3 is to find the minimum value of expectation energy. For that, you have to differentiate this E with respect to the variation parameter. Okay, suppose I'll take one variation parameter alpha. Differentiate E with respect to alpha and put the value equal to 0. If you put the value equal to 0, you will get one particular value of alpha that gives you the minimum possible energy. So I'll take alpha minimum. Substitute this alpha minimum in the expectation energy formula. So step 4 is calculate the minimum energy using this alpha value. We'll discuss, right? So we'll get some alpha E, substitute this alpha E in this E, alpha minimum in this E, you can get the minimum possible energy from variation method. Then this is the most important step. Most important step is that compare this minimum energy, calculated energy, with the exact ground state energy of the system. Listen, this is calculated minimum energy. Compare this with the exact energy. Listen, according to variation theorem, the calculated energy, most of the time it is greater than the actual energy. Very rarely it is equal to Eg. This is what we call as Rayleigh-Ritz variation principle. Rayleigh-Ritz variation principle, also called variation theorem. Right? Using variation method, if you calculate minimum possible energy, that energy will be most of the time greater than the actual ground state energy. Rarely it is equal to ground state energy. Now consider particle in a 1D box. 1D box. Okay, now I'll take the ground state. Right, for ground state, n is equal to 1. For n is equal to 1, you know the wave function. How the wave function vary? Is it in the actual system, the wave function increases and reaches 0. So this is the wave function plot for the ground state. Now, the exact wave function we know already, because 1D box is exactly solvable. For 1D box, what is the exact wave function of ground state? We know that square root of 2 by L sine n value is 1, so plus n pi by L into x.
Yes.
This is the exact ground state wave function, and we also know what is the exact ground state energy, h square by correct? N value is 1. So h square by 8 ml square is the exact ground state energy. This we know already. But I am going to assume that this is an unknown system. And I am going to calculate the energy. Right? So let me guess. I am going to use a variation method. Okay. So first step is guess your trial wave function for the system. Listen. My trial wave function should obey the boundary condition. What is the boundary condition? At x equal to 0, wave function should be 0. At x is equal to L, the wave function should be 0. Right? When we move from 0 to L, wave function should increase and then decrease. Right? Yes. To match with this, we should give some mathematical equation. Yes, just try and tell me. I'll tell you. Listen, what to do? Listen. I'll give some function like this, x into L minus x. X into L minus x. Just check whether this formula obeys this boundary condition or not. So this is the trial wave function, and we know what is the Hamiltonian operator. Hamiltonian operator for particle in 1D box is minus h square by 8 pi square m d square by dx square. This is the kinetic energy, and we assume that potential energy inside the box is 0. So this is the Hamiltonian. Now we'll use this formula in the variation method. So according to variation method, okay, the expectation energy or the average energy is equal to, right, is given by the formula psi 1, bra of psi 1, Hamiltonian operator, and ket of psi 1 divided by bra of psi 1 and ket of psi 1. Okay, this is nothing but integral. I have told you already. What is this? This is nothing but an integral. The limit is 0 to L. 0 to L. What is psi 1? Psi 1 is x into L minus x. What is the Hamiltonian operator? Hamiltonian operator is minus x square by 8 pi square m into d square by dx square. Okay, then into psi 1 again. Psi 1 is x into L minus x. Since it is 1D box, you should put dx. Divided by square root of 0 is divided by 0 to L, integral 0 to L. Then we have x. See, here we have psi 1 and here also we have psi 1. So we get x square L minus x the whole square into dx. Okay, take this. I'll keep. So the expectation energy is equal to, right, I'll keep minus h square by 8 pi square m out, integral 0 to L, then we have x into L minus x, then we have an operator d square by dx square, and again x into L minus x. So if you multiply inside, I'll get Lx minus x square into dx, divided by, in the denominator we have 0 to L, x square, L minus x the whole square into dx. Okay, now first we apply this operator here. What is meant by that? We should differentiate these two types. So I have Lx minus x square, Lx minus x square. Now you have to differentiate these two types, d square by dx square. We have to differentiate these two types. So first we will do differentiation by one time. X, if you differentiate, you will get 1 CL. X square on differentiation will be 2x. Differentiate this again. L is a constant, it becomes 0. So I will get minus 2. So if you apply this operator on this function, you will get simply minus 2. Anyway, minus 2 is constant, you can take it out. So I will get minus or minus plus. So expectation energy equal to 2h square by 8 pi square m integral 0 to x into L minus x, then we get dx here, divided by, in the denominator, 0 to x square into L minus x the whole square into dx. Okay, take it. So if you simplify this, we end up with 1.014 into h square by 8 m square. So this is a variational energy, or energy calculated using variation method. This energy, right, is greater than the actual ground state energy of one particle in 1D box. Okay, But it is slightly greater, see 1.014. It is slightly greater because we have chosen a function which obeys the boundary condition. Right, so it is somewhat close. Right? Take it. Listen, this formula is applicable for any system containing 1s n electron. 1s n electron system. Okay, if electron present in 1s orbital, then you can use this formula. Right, electron present only in 1s orbital, no other orbitals. Okay, so for 1s1 configuration or 1s2, right, we can calculate the expectation energy directly. Right, 1s1 is nothing but hydrogen atom, 1s2 is helium, right, helium. Okay, how to calculate the expectation energy directly? Isn't expectation energy is equal to, this is the method we follow. Expectation energy E is equal to n into, n is nothing but number of electrons into kinetic energy plus number of electrons into Coulombic attraction energy, Coulomb attraction energy. Just write down and tell you how to do what is meant by all these things. Then plus number of electron pairs. M is number of electron pairs. Electron pairs which repel each other. M number of electron pairs into Coulombic or inter-electronic repulsion energy. Inter-electronic repulsion energy. Okay, take note. Here, n is number of electrons. Kinetic energy is given by alpha square by 2. Let me write here alpha square by 2, where alpha is called variation parameter. Alpha is the variation parameter. Right? It is also called as effective nuclear charge. Effective nuclear charge. Right? Variation parameter, it is also sometimes called as effective nuclear charge. Alpha. Kinetic energy is alpha square by 2 plus n into number of electrons into Coulombic attraction energy is nothing but minus number of protons. Listen, minus number of protons into the Coulombic attraction term. Minus the number of protons into alpha. So I will take this is number of protons, right, into alpha. Okay, take it. Number of protons into alpha. This is Coulombic attraction energy, which is actually minus, plus electron pair into this is inter-electronic repulsion. The repulsion energy between one pair. Repulsion energy between one pair is 5 by 8 into alpha. Okay, take this. So suppose I'll take hydrogen atom. Now I'm going to apply variation method. To hydrogen atom, and I'm going to find the ground state energy. Okay, ground state energy. Right? Listen, what is the first system? Trial wave function for the ground state. Trial wave function. Let me guess a trial wave function like this. Ut is equal to e power minus alpha into r. Don't worry about the normalization constant r. When you normalize, it will come automatically. Okay, alpha is nothing but variation parameter. Okay, now if you use the expectation energy formulas, if you substitute and if you solve it, finally you will end up here. So what is that? Expectation energy E is equal to, now for hydrogen atom the electronic configuration is 1s1, right? So we have only one electron, so put n equal to 1 into alpha square by 2 plus we have only one electron, 1 into, and the nucleus has only one proton, right? Hydrogen atom has only one proton, So number of proton is 1. 1 into alpha is alpha, so minus alpha. And since there is only one electron, electron repulsion is 0 because there is only one electron. So this term becomes 0. So what we left with is E is equal to alpha square by 2 minus alpha. See, differentiate this E with respect to alpha and put the value equal 0 so that you will get the minimum possible energy. Okay, so if you differentiate this, alpha square, if you differentiate, you get 2 alpha, 2 cancels, you will get just alpha, minus alpha, if you differentiate, you get 1. Alpha minus 1 equals 0 or alpha equal to 1. So what does it indicate? When alpha is 1, you will get the minimum possible energy. Therefore, what is the minimum energy? Therefore, E minimum is equal to, in the place of alpha you put 1. So, alpha square 1 by 2 minus 1. You get minus 1 by 2 atomic unit. We get energy in atomic unit. Okay. See, we have a nucleus. Nucleus charge is plus 2e, but I will put alpha e. Okay, where alpha is the effective nucleus charge. And we have 2 electrons now. 2 electron 1, this electron 2. But for both electron, charge is minus e only. This is distance between the nucleus and the electron 1. Let me take this R1. And this is distance between the nucleus and the electron 2. Let me take R2. And this is the distance between the 2 electrons. Let me take this R1. Okay, this is the distance between the 2 electrons. Now, listen, we need to guess a trial wave function for the ground state. So our goal is to find ground state energy. So what is the trial wave function for the ground state? I have 2 electrons, but what is the ground state configuration of helium atom? Ground state configuration
1s2.
Configuration 1s2, right? So both the electrons are present in 1s orbital. Both the electrons are present in 1s orbital. So what I am going to do, I will take, listen, 1s orbital wave function for electron 1 and I will take 1s orbital wave function for electron 2 also, because both the electrons are present in 1s orbital. So take 1s orbital wave function for electron 1 and 1s orbital wave function for electron 2. Listen, 1s orbital wave function for helium atom we don't know. We know only 1s orbital for hydrogen. So what I am going to do, for 1s orbital of helium, instead of helium wave function, we don't know what is that. So instead of that, I am going to choose hydrogen atom. Okay, this is what we call as basis function. What's the basis I am choosing? What is the basis? I am going to choose hydrogenic basis. Hydrogenic basis I am going to use. What is meant by that? Instead of 1s orbital of helium atom, I am going to use 1s orbital wave function for hydrogen atom. Okay, because we don't know what is the wave function of 1s orbital of helium. That we don't know. So, the trial wave function can be given as 1s orbital of hydrogen atom for electron 1 and 1s orbital of hydrogen atom for electron 2. Okay, and what is the hydrogen atom 1s orbital wave function? That we know already. It consists of some normalization constants and all. Right, e power minus alpha r term will be there. Okay, right, so I am not going to write, I will just simply like this, instead of equal, I will put proportionality, it is proportionality, some constant will be there, e power minus alpha into r1 and e power minus alpha into r2 will get, this is proportionality, e power minus, you take alpha as common, r1 plus r2. This is my trial wave function. Under hydrogenic basis, this is the trial wave function. Alright. So expectation energy is equal to 2, we have 2 electrons, 2 into alpha square by 2, this is the kinetic energy for each electron. Then plus 2, we have 2 electrons into the nucleus charges, isn't the nucleus
minus.
charges minus, there are 2 protons, so 2 into alpha, right?
Sir, இங்க என்னங்கிறது என்னங்க சார்?
1 now, 2 electrons, so we have 1 pair. M represents electron pair. I have only 2 electrons, so I have 1 pair of electrons into 5 by 8 alpha.
5 by 8
this is
alpha.
repulsive energy. So what we get is E is equal to, these 2 cancels will be alpha square minus 4 alpha plus 5 by 8 alpha. Take LCM here. E is equal to, you keep alpha square as such, take LCM here. So 8 4s are 32. 32 minus 32 plus 5. Am I right? Just check it. So differentiate this E with respect to alpha and put the value equal to 0. Alpha square, if you differentiate, you get 2 alpha minus, if you differentiate alpha, you will get 1. 1 into 27 by 8 is 27 by 8 equal to 0. 2 alpha equal to 27 by 8 or alpha is equal to 27 by 16. 27 by 16. Okay. 27 by 16, right, is comes out as, let me show you,
1.68.
27 by 27 divided by 16. Yes, it comes out as 1.6875. 1.6875. We write roughly 1.69. What is alpha actually? What is alpha? So what is the minimum energy? E minimum equal to, in the place of alpha, I put 1.69 square minus 27 by 8 into 1.69. Okay. I use calculator and tell you the value. You will get the value in atomic unit. Let me do it. 1.69 into 1.69, which comes out as 2.8561 minus, and this value 27 by 8 into 1.69. It comes out as 5.7037 minus 2.8561 will give me minus 2.8475 atomic unit. Minus 2.8475 atomic unit. This is the minimum energy calculated using variation method. Now, this is an atomic unit. If you convert into electron volt, multiply this value by 27.21, 2.8475 into 27.21. I am getting the answer as minus 77.48 electron volt per atom. This is the minimum energy or ground state energy calculated using variation method. But what is the actual ground state energy? Actual ground state energy for helium atom is minus 79 electron volt. Minus 78. But anyway, the values are very close, correct?